Hello students, welcome to online lecture series of discrete mathematics. Now, today we will see what is a spanning tree. So in previous sessions, we already studied the spanning subgraph. Right? So same as the spanning subgraph, this is a spanning tree. So what is this spanning tree? A subgraph T of a connected graph G. It's called a spanning tree of G if T is a tree and T includes all the vertices of G. What? T is a tree and T includes all the vertices of G. So whatever this subgraph is there, right? So this subgraph must contain all the vertices of the graph, all the vertices of the graph. And we know the tree doesn't contain any circuit or a cycle. So we can say this is an open path. Open path is there for a tree. So for spanning tree, right? So this spanning tree contain all the vertices of the graph. So see here, this is the graph. This is the graph, and this one is the subgraph of this one, and we can say this is a spanning tree. So here contain all the vertices 1, 2, and 3. 1, 2, and 3. Same again. Suppose this 1, 2, 3, and 4. So spanning tree for this. How many spanning trees we can draw? Like this one also. Again. This one. Again. This one. Again. This one. So the different spanning tree is 1, 3, 1, 2. So there are the different spanning trees for the this given a graph. So this contains all the vertices of the graph. So suppose G is a connected weighted graph and each edge of G is assigned a non-negative number called weight of the edge. Then any spanning tree T of G is assigned a total weight obtained by adding the weight of the edge in a tree. So here minimum spanning tree of a G is a tree whose total weight is as small as possible. So whatever spanning trees we have drawn, right? Different spanning using any graph, we can draw a number of spanning trees for that graph. So whatever number of spanning trees is there. So if there is a weight for every edge in the spanning tree, and whatever spanning trees are there, so you have to calculate the weight of the every spanning tree. Whenever we calculate the weight of the every spanning tree, then the minimum weighted spanning tree is nothing but the minimum spanning tree of that graph. Minimum spanning tree of that graph. So same example we'll see here. Suppose this is the graph, and these are the different spanning trees. So this is weight 1, this one is 4, this one is 3. Again, this one is 1, this one is 2, and again this one is 3. Suppose this one is 4, 3, and 2. So for these 3 spanning trees, right? Which one is a minimum spanning tree? So we have to calculate the weight of the spanning tree. So 4 plus 1, 5, 5 plus 1, 3, 8. Here 3 plus 2, 5, 5 plus 1, 6. Here 4 plus 3, 3 plus 2, that is 9. So here 8, 6 and 9. Minimum is this one. So this is your minimum spanning tree. Whose weight is 6. Whose weight is 6, which is a minimum. Which is a minimum. Next, the Kruskal algorithm to find a minimum spanning tree. So there are two algorithms to use to find out the minimum spanning tree. One is a Kruskal and second one is a Prim's. Second one is a Prim's algorithm. So this algorithm finds the minimum spanning tree of a T of a given connected weighted graph G. This Kruskal algorithm. So here first input given connected weighted graph G with n vertices, whose minimum spanning tree T we want to find. So order of all edges of the graph G according to increasing weights. Third, initialize the T with all vertices, but do include an edge. Fourth, add each of the graph G in T which does not form a cycle until n-1 edges are added. So here for Kruskal, just here we have to find out the minimum weight, minimum weighted edge for the given spanning tree, right? Or you can say for a given graph, we have to find out the minimum weighted edge. So just we have to write down that minimum weighted edge means, or we have to write down that edges in an increasing order. So whatever minimum weighted edge is there, so draw that edge, right? Again, next find out the minimum weighted edge. Again, draw that edge, right? So just here we have to find out the minimum weighted edges, right? In increasing order. In increasing order, we will see an example. So how to find out the minimum spanning tree. So here this is the example, that is determine the minimum spanning tree of weighted graph as shown in figure. So for this diagram, see here. So which one is the minimum weight here? Minimum weight is first is 2, that is this one, right? Second 3, next this one is 4 and so this 4 and 4. Next 5 and 5, so it's 5. Next 6, so 6, and last that is a 7. That is 6. Last that is a 7. So this is the increasing order, right? So just we have to draw this edges. So here so 2, 3, 4, 5, 6 and 7. So, yeah, first we have, so we add this the minimum weight 2, that is B2E. Next we add this 3, that is B2C. Next we add 4, that is C2F. Next we add, that is again 4, A2D. So you can add any one, that is either C2F or A2D, because both edges, right? Both edges containing the same weight. So you can add any one, that is either AD or CF. So here first we add CF, then AD here. Next, so next minimum is 5, C2D, C2D. So minimum spanning tree form in a step 5 is output and total cost. So why we stop here? Because what is the minimum spanning tree? What is a spanning tree? Spanning tree contain all the vertices of the graph, all the vertices of that graph without any circuit or a cycle, without any circuit or a cycle. So here, whenever we take this B to C 5, so all the vertices, right? So all the vertices are in spanning tree, right? So here, and this is a connected spanning tree, connected tree, right? So for weight or total cost of the spanning tree, you have to just addition of this all the weights. Is 5 plus 4 plus 3 plus 2 plus 4. So that is equal to 18. So total cost of this minimum spanning tree is 18 using Kruskal's algorithm. So we'll stop here. In next session, we'll see the next one.